So last time we talked about maps. We first talked about projections and why projections are important. And then we talked about choropleth maps and proportional stimulus maps. And for choropleth maps, we discussed this problem of having, having shapes of a size that is not really controlled by the data, but rather by the shape of the area that you want to visualize. And so this is like a technique that was published at Infobis a while ago. These are called necklace maps, and I handed out like a sheet with instructions. Like you have two different graphs on there. You have a necklace map of illegal immigrants in the United States and the migration in the Netherlands. And so the next 5 to 10 minutes, please talk to like a partner and try to answer those questions and then like make your usual analysis of these visualizations.
Color coded, and then what percents are encoded with, I'm guessing, or areas. I think they're just to be close to the states, and then you use a color, like a mapping visual with the color. It's probably just like an algorithm close to representing. They're pretty close. It doesn't take too long to find which one it is. So the number of immigrants is encoded by percentage. There's no in thousand. So if they have less than 500, I guess they. Yeah. Okay. Well, in that case. I don't know. It's kind of weird to put some of these next to each other, right? Because like the size of like Texas, you know what I mean? Like if it's 5,000, like Texas is 3 times as big as Texas is number in thousands. It's like I first looked at this and you go to like percent. Yeah, like I think encoding it by just the absolute count of thousands of just the numbers. But then again, I guess like that assumption is really compare states. Or yeah, we're a table with the raw counts. A table with the ratio to area, ratio to population. Clicking the table title, you just sort of by that. Yeah.
Okay, so let's talk about this for a bit. So the first question here was, what is the purpose of the disks?
The portion of the emittance basically the scale.
Exactly. So what we have in the first example with the immigration, we have a count of immigrants, and we can see that they're the bubbles are scaled, or the disks are scaled proportionally to the number of immigrants that are illegal immigrants that are living in a state. And so let's take a step back. What are the marks and channels that are being used here? Please raise your hands.
6 or 7 months.
The circle, sorry?
The marks.
Are the marks? Yes, that's correct. Other marks?
Size.
That's the channel. The size is the channel. Other marks?
Areas on the map.
Sorry, what's that?
The map.
The map? Yes, so the shapes, like the shapes of the states. So the map is also a channel, a mark, sorry. What are the channels? We had
The size of the circle.
the size of the circles, and the other one? The color. And so what does the color encode? Is it a relation between? Yeah, so the color here is really like a label only. Like, what does the position of the circles encode? They're not arbitrarily positioned, right?
I think maybe the region in US, like the New England section, Midwest and West, West side and East side.
Yeah, that, implicitly, but more explicitly. Like it's not a very precise measure, right? But they essentially nest a couple of circles or arches on this map, and then they position the circles on the circumference of the circle as close as possible to the state that it's associated with, right? So we have Texas, which actually fits into Texas. We have Arizona, which fits into Arizona, but Nevada, for example, is as close as possible to its circle, but it actually doesn't overlap. So what problem are they trying to address here? Like, what would be the obvious alternative?
To put the circles in on the state itself,
Exactly, and why would that be a problem?
because some states are too small.
Exactly. So if you look at Rhode Island over here, the circle for Rhode Island is a lot bigger than Rhode Island itself. And then there's the neighboring Massachusetts, the neighboring Connecticut, and so you couldn't really place all of those next to each other. So this technique is really not particularly relevant if you have enough space, like if you only have a couple of, let's say, states, and you have enough space to put those circles into them. But if you have a map like this, then like laying them out in this way is a potential solution. What is going on in the second map here? Like, do we have extra marks and channels?
Yes.
Yes. Which ones?
Arrows.
Arrows. Okay, the arrows are the marks, and what is the channel here? The width of the edges of the arrows encodes how many people are migrating from one area to the other one, and the circle size encodes the size of the population in the first place. It's not particularly surprising. the bigger circles, the bigger regions in the Netherlands also have like the big arrows associated with them. So what are kind of like some trends that we can see? We see, like, unfortunately my Netherlands geography isn't great enough to tell you the names of those areas, but ZA seems to be, there's a lot of people moving out of that area and not a lot of people moving into it, right? Okay, so do you find this visualization effective? I see somebody like say yes, some say no. Comments? Anybody have like any opinions?
So for the chart on the left, I feel like it might be better to do a hybrid version where you can simply place the circles on the states where possible, and where not you use the necklace.
Yeah.
That would make it a lot easier to map the labels to the states as well.
I feel like it's effective if you're looking for a particular state. So if you're like, I want to see the size of Utah, you can find it pretty easily if you know where the state is. But it doesn't, you have a hard time showing an overall, like, which one's biggest. Like, I'm guessing California, you know, it's hard to tell overall trends.
Yeah.
It looks like you can make relative comparisons, but there's no actual data as to how many.
Yeah, so there's actually a legend missing here, right? So that's a big problem.
I feel like the sheer number of colors is confusing. Looking at it, it's like there are duplicates in colors.
Yeah, many actually. Kansas and Florida and Indiana all have the same color, right? So they're using color for labeling. And like, what would be, like, if you wanted to avoid any collisions of these circles, what could you do instead?
Use a gradient color probably.
What do you mean?
Probably like
Like a choropleth map. But like, if you want to use the circles.
I mean, it's a combination of circles and colors, like using some gradients in that and then.
Yeah, so the other approach that you could take is you could essentially have like a force-based system here, right? That you try to place every circle as close to its state as possible. And if it doesn't fit into the state or it has to be pushed away, you could simply like have a label pointing inwards. And then you might not have to use color. And so you would probably be fine in the west here where the states are big and the population isn't that big. And then you would have a lot of labels or a lot of like arrows pointing to the states, which is kind of like what we see in a lot of maps, like where like Rhode Island is pointed out explicitly. So like other opinions about this visualization? Have you seen something like this before? This paper is a couple of years old, so that also tells us that this hasn't been adopted much, right? And one of the problems that the technique has, it's kind of quite manual. So you actually have to tell the algorithm where to put the circles. The algorithm then will figure out where to place the disks on top of the circles, but it doesn't figure out how to place these larger circles in the first place. Here's another example, and like a comparison of where such a visualization technique can be. Like, this is another technique that we're talking about later, where we rescale the area. And so like, one of the problems of rescaling the area is obviously that if the data is small in certain areas, like this is internet users in Africa, if the data is small, essentially we kind of lose all of the geography here. Of course, here we keep the geography, and we see that internet usage is really almost non-existent in much of Central Africa. Okay, so that kind of leads us right into cartograms, and cartograms is also what you're using in your homework this time. So again, we're trying to balance the size versus data effect that we've discussed at the beginning of the last lecture. So where we have this disproportionality of like the pixels that are of a certain type and the data that corresponds to it. So like here, the actual data proportions compared to the pixel proportions, and you can see that there's quite a difference here. So what if we just change the size on the map? Essentially try to find a compromise between geospatial accuracy and quality of data encoding. Like, that's the promise of cartograms. So here is a hand-drawn example of the number of Elvis concerts that Elvis gave in the various states across the US, rescaled in attendance per state. And so you can see that he gave a lot of context in in Tennessee, in Texas, also in California, but he didn't come much to Utah. And so, what do you think about this visualization? What's that?
It's a nice one.
It's a nice one. What, like, do you think the compromise between geospatial context and the size of the areas here is appropriate?
I mean, if you know the state size, it's a prerequisite knowledge. You know like how big each state is, so you can kind of use it as a information to kind of connect the.
Yeah, so I think it's neat, it's engaging, but of course, whenever you rescale area by data and you kind of like don't have a good proportion of area to data, then it gets a little tricky. As you can see here, like there's a big white chunk here, and so we get a good sense of what is going on. Also, what's the problem of these irregular shapes? Do you think there were more concerts or more attendees in California than in Tennessee?
It's hard to compare when there is a difference like that in the shape.
Exactly. So this is kind of a downside, and it's like it ties back into what I said at the beginning of the last lecture, that you should only use geospatial like a geospatial layout if the geospatial layout is actually paramount. Here's another example that scales the distance by data, in this case travel time on an airline. And so we can see that, well, what kind of examples do we have here? It looks like there are pretty good connections from Los Angeles to the Texas area, from California to Texas, for example. And so this is basically like if I didn't have any labels here, you might not be able to recognize that this is the United States, right? So this is like very, very abstract already, and yeah, it's tricky. This is kind of like, well, not quite what you're doing in your homework, but a little bit more like what you're doing in your homework. Like in your homework, we're actually using color and regular shapes, which is even easier. But here, this guy used, and that's clearly not 2016. I forgot what it was, but it was, I think, 1916. 1916. Because Austrian-Hungarian Empire does not exist anymore. So here, this is a world population map in 1916, and like here they use rectangular shapes to represent the populations, and they also still kind of retain some of the context. So it's a little bit similar to the necklace maps to some degree, but they kind of give up the explicit spatial context. What do you think about this representation?
I like it much more than the necklace one.
Yeah.
But also you lose out on the entire map feeling of it.
Yeah, so you lose all of the specific spatial information, right? You essentially have a grouping by continents, and not much more here. But I also do like this visualization. The regular shapes help us also to see the differences better. So we can see that the Chinese Empire had a bigger population than the Indian Empire. We can see that the United States was really small compared to what it is now, like with only 90,000 people. And then almost like Germany being almost the same size as the United States, which is Germany at this time had 64 million people. Now there's about 80 million people in Germany. The United States at that time had 90 million people, and now there's about 300 million people. So these things have changed quite a bit. But I really like this, and this is from the time, and of course this is hand-drawn. Here is a recent world population map. Interesting to see here is Canada is only a sliver along the border, which also makes sense from where people live in Canada. And the same, Russia is only a sliver on top of China here. And here's an example of a New York Times article that lets you do these things for different aspects. So here we have what your global neighbors are buying, how much we are spending for different articles. So here we have, let me zoom in a bit. We have clothing and footwear right now, and you can see that the Americans spend a lot of money on clothing and footwear, but Indians, for example, don't spend a lot of money on that. If we switch over to electronics, we can see that people generally spend less on electronics than they spend on clothing. The alcohol and tobacco suddenly sees Europe rise. So Americans don't seem to smoke and drink as much. Household goods, like that's the second and third lawnmower in the United States probably. And then recreation, and you can suddenly see that Japan has actually increased quite a bit here. And so what do you think about this visualization? Like, I do like the individual ones, right? But the comparison is really hard. I really would be interested in getting a better sense of like where do the countries spend their majority of their money on, and here I have to switch between them and then manually have to consciously have to track, okay, how are these countries behaving right now? And so this is a little tricky, but generally this is a nice visualization. And this is from 2008. The basic idea of the next technique here is to really like take the shape of the world and distort it and to try to be as faithful to the shape itself, but distorted by the data that you want to map on top of it. So this is just the world in geography, in its geographical dimensions, and now this is rescaled to population. And we see, of course, like the India and China here being much bigger, and Brazil being about the size it looks for real. So like South America seems to be pretty faithfully transitioning, but here we see the same thing with Russia being tiny, Canada being tiny, and so on. Here this is the same map for GDP, and we can see that this is now like almost unreadable, right? Especially here in like Central Asia, it's really hard to see what is going on in Africa. You wouldn't even be able to read an individual country. Child mortality. You see that the child mortality in industrialized countries is pretty low. Greenhouse emissions. Kerry versus Bush. So what do you think about these maps? I think they make an interesting point, right? But they kind of it's interesting to look at the map like this and to see where those countries are placed, but it's not like a super faithful data visualization, right? So you could do this in a better way, but of course they have a quite interesting dramatic effect. So especially if you look at greenhouse emissions, and you can see where those greenhouse emissions are, and so on. And so if you want to learn more, there's like a link on the slides to the actual visualization technique. And this is again using shapes for all of those different districts in the United States for the Bush versus Kerry race. But here, like the geospatial context is really like only very vaguely represented. Okay, so next I wanted to talk about flow maps. Flow maps are like, probably like in high school you have probably had these like big rollout maps where your geography teacher has shown you like how people have migrated and so on. And this is what we're talking about when we talk about flow maps. So some flow between geospatial locations. So this is here an early flow map, the transportation of passengers in Ireland. So you can see that like the width of these like flows here corresponds to how many people travel to and from Dublin. You can see that this here is like the most important path into Dublin compared to like others that go up to the north that are not as important. You have probably seen this one. This is often like hailed as the best infographic ever made. This is by Charles Minard from 1869, and it shows Napoleon's March in Russia. I think I have kind of like explained this in my introductory slides already, but just to recap, like what happens here is like we have geospatial context of how Napoleon's army marched from Europe to Russia to Moscow, and the width of these let's say flows here encodes how big the army was, and you can essentially see very well that they actually didn't lose a lot of people in the actual fight on Moscow, but instead they lost a lot of people on the way and on the way back, so that only a tiny sliver of the soldiers that were in Napoleon's army came back alive to France. And it also juxtaposes it with other data like the temperature on the retreat that kind of like highlights why there's so many people who perished. Here is a visualization for the effect of the US Civil War on the cotton trade. So you have the trade before from England to the United States. You can see that there is like a very, very dominant pattern of cotton trade between the US to Great Britain and to other parts of Europe. But after the Civil War, you can see that the trade to the United States essentially died down, and instead the trade to Asia intensified significantly. Here is a visualization of, let's see what it is. Works. Oh no. Oh well. So this is a visualization of immigration path between different areas in the United States. So this is interactive. You can hover over any area that you want to. And so here I've highlighted Plymouth County, Massachusetts, and I'm looking at where people are moving. And so here the intensity of the ribbons, or is probably, well, the color intensity of the destinations probably encodes the data. However, like this is a non-spatial representation of the same kind of data. So here we kind of can interactively select and see this specific geospatial context. Here we have a New York Times visualization of people people who live in Utah, where they're from, but even across time. And so you can see from 1900 to 2012, the majority of people who live in Utah were actually also born in Utah. And then we see that in the 1900s, the majority of immigrants were born outside of the United States, which kind of is taken over by other states in the West and California and Idaho as we go along. And these ribbons, they are in some way ranked by their size. It doesn't seem completely faithful because we have Idaho here, but they're supposed to be ordered and essentially crossing over when they change in rank order. And this is actually a pretty neat visualization. You can look at various states, and you can see these trends across all of the US states, and they have also done some smart aggregation here because they don't show you all of the 50 states. If they can group them based on regions where people are moving from, they do that. So move to other states in the West, move to other states in the South, and we can switch between migration into and out of. So you can see that Californians tend to stay in California, but other people tend to move into California. And so we see this trend that people like internationals made up a big percentage of immigrants in the 1900s, but then it dipped in the 60s, and now we're back again at the levels of the 1900s, for example. And you can see that migration patterns, like the big Midwestern migration to California, is kind of slowing down in terms of percentages. You can scroll through other states, and you can look at those, at the immigration and at the emigration from those states. So compared to those two charts where I had the big map with the explicit links and something like this, what do you think? Which is the better representation of this data?
This one.
Why?
I mean, you have a high-level picture, then you can drill down and kind of move around and get whatever data you need from it.
Yeah, and also what did the other visualization show us? It showed us only one time point, right? And because we're not using the geospatial context here, we have actually a lot more space to show how that changed over time. So we can show a lot more data by giving up the geospatial context and representing it with those ribbons here. So I do like this visualization quite a lot, and it's fun to play with. And you can also like click on any of the states. And if we click on Utah, like people who are living in Utah were born, like 62% in Utah, and people who moved out of Utah moved either to California, to Idaho, to other states in the West. So like Utahns seem to like to stay on the western side of the United States and don't usually move into the east. Like northeast is really tiny, for example. I do like this visualization here. This is a flow chart that shows us the rail freight tonnage. How many tons of freight are transported along certain rail tracks. So here we have a geospatial context that is pretty precise, and the width of these routes here corresponds to the overall volume. And we see that there is like a massive gravitation towards like the Midwest here, which is where a lot of coal is being shipped around. And this is from this Maps of American Infrastructure, which is really like a really great piece in the Washington Post. So there's a lot of interesting maps in here. I just picked the freight one because it's the only one that really does something with data, and the other one mainly shows us locations. So bridges in need of repair and so on. So this is pretty informative. So I recommend that you look through that. Here we have, anybody want to guess what I'm showing here? If you know what it is, it's easy to recognize, but this dot here is Paris. And it's flight patterns into and out of Paris. And they are actually live tracked. And this is an interactive system where like flights, of course, are in 3 dimensions. So this is like live tracking or like it's not live tracking, but it's actual flight data sped up. But what is nice about the system is that you can like do various filters, various brushes, and like dig into individual flights. And so here, like this also shows us this is a very flexible system. I can map anything to an X and the Y coordinate. I can map anything to a color. And so here, altitude is mapped to color. Now that it's turned off, now altitude is mapped to the Y-axis. And so here you can now see like the flight path, these like discrete heights at which planes travel, and then going down into airports. And you can also do this dynamically here. So now this guy's brushing all of the flights that came from the Atlantic, and you can already see that the majority here land in Paris. And here you can see like how they come down from these flight paths. So this is a pretty neat system, and these kinds of like 3-dimensional data are tricky to visualize. Of course, what we're missing here is like the labels, right? So if I didn't tell you that this was Paris or France, you still wouldn't know what you're looking at. But it's still a pretty neat system. This is like one of my favorite papers on geospatial flow visualization. Like, I think this really is one of the smartest ways of thinking about this. Like, what you kind of like have both the exact geospatial layout here. Like I think this is also migration between those different states. But then, like similar to the system that I just showed you, you can highlight regions and you only see the flow between those regions. But then if you say, oh, the geospatial context isn't that important, I can simply aggregate that away. You can transition between a network like this to an abstract network like this. So you can see that within the Washington area, like there's a lot of migration or a lot of people moving around within the Washington area. And then we see that between Washington and Arizona, we have about an equal transition between people moving in and moving out. We see that a lot of people move from New York to Florida, probably like people when they're retired move to Florida, and there's also, of course, people moving within Florida and so on. And so this is really a very smart way of thinking about what is the important piece of information and giving users the power to represent it. And they also use these little spaces here to show us data about what we see in those regions. So histograms, parallel coordinates plots, scatter plots, or even tree maps. And so this is very flexible. Let me show this briefly.
The affected ranges in the attribute view are updated. Selections can also be controlled with the centered widgets. We can also set ranges for non-projected attributes. Now we add another selection. Initially, edges within a selection and between selections are shown. These edge attributes can be changed similar to the node attributes and are treated as a nominal edge attribute. Here we show some examples of enabling and disabling different edge types, such as between and background edges. Now we also filter the second selection on a non-projected attribute and rename both selections. The selection labels are also shown in the overview boxes. By changing the projection, all selection boxes are updated to the defined ranges. Note that earlier set.
Okay, so you get the idea. This is like a super flexible system for data exploration. Of course, it's not something that you would give to an end user necessarily. Okay, next I wanted to talk a little bit about data-driven maps. So the idea here is don't use a map to render on top, but let the data make up the map. A simple example, what's happening here is that we don't show any borders, or we don't even show where there's land and sea. What we show is simply dots that are geolocated. And if you have enough of those dots, you usually can make a nice map, as you've seen in the last example and as you see here. Here is a dot for every zip code in the United States. And magically, geolocating every zip code in the United States makes up a pretty nice shape of the map. Here is a map for every person in the northeast region around Boston. And so, even though you don't have data here, where are cities, where does the ocean start, you can see pretty clearly the structure of the geography, and these are pretty impressive pictures. This is a map that connects every zip code to the subsequent zip code. And so suddenly you get you can actually start to see the boundaries between states. This is a map of taxi drop-offs in New York City. Again, without any background map or any background structure. And you can see very clearly that lots of people are being dropped off in Manhattan and in certain regions. This is a map that is a little bit similar to what I showed you just earlier with this aggregate flow visualization. But this is also just using these particles. So let me show you this video quickly.
Project Sundance is all about data visualization. How do we make sense of all the massive amounts of data around us? We use principles of information visualization to make it easy to understand the data and see the patterns within the data. So let's take a look at this data set here. These are actually 50,000 counties, but there's information, there's structure in this data. So if we actually map it onto a map, we can actually see the structure showing up. And when we actually shift to a histogram, the motion really helps you understand the data. And if we switch back to that, where they go back to. So we're going to actually look at some results from the recent election. So here what I'm going to do is map onto each county how they voted. And you can see actually the blue counties and red counties, and it looks pretty extreme. But actually it's much more nuanced than this. So if we look at a different palette here, you can see that Yes, it's blue and red, but it's not quite so extreme on either case. And in fact, we can even break this apart and actually look at 9 different graphs. Here are the most extreme on one side, the most extreme on the other side. So if we actually select a point over here and we get some information about it, we can see that that was Texas. So that's looking at elections, but there are a lot of other things that we can look at besides elections. So we can look at per capita income. So here's the per capita income, and you see a big swath of red across the country. If we actually kind of looked at that in a histogram here, you can see that there are very few counties that have a high per capita income, lots that have a much lower area. So we're interacting with this in a very natural way.
So the idea here is that every item is represented as a pixel, and what they're doing is just rearranging those pixels according to various rules and coloring them according to various data points. And by doing that, you can do smooth transitions between the geographic layout, as you saw on the map, and a histogram like this. And so this is a pretty intriguing technique, I think, which is kind of like easy to understand and follow along what is going on. Okay, and the next section is only like, yeah, these are just fun maps that people, of course, use where they use maps as an analogy. Like here, you probably remember this map of the island. You can have the map of the internet in 2007 according to XKCD. You have the MySpace area and the IC North, Yahoo, and Windows Live, which is then updated in 2010, where Facebook has taken up a big chunk and Farmville was still popular. And Twitter and Skype is also appearing. You can have maps that are not like on the inside of a building, instead of having maps that are like geographical. So here is tracking of people and the house cat, where they were in within a couple of hours in a living room while the TV was on. And then this is a map of London in a very abstract sense. Okay. So that concludes maps, and now we're moving on to graphs. And for graphs, I want to start out with you trying to come up with graph visualization techniques yourself. So we'll run an exercise. I'll be handing this out. So what you're supposed to be doing here is take a look at this data set. This is a co-author graph where we give you a couple of people and how many papers they co-authored. And you should come up with 2 different designs for representing this data. I'll give you 10 minutes in a group, and I also have scratch paper at the desk in front. Okay. Any paper? else that I missed?
Everyone on both sides. Especially if we have this co-opted constraint. Yeah. Or we can just do I guess another option would be do an arrow. You want it explicit. Because also you could change the size of the nodes based on your paper, so then you also can show the number of yeah. I'd like to get that so you can change the size of the edges based on the yeah. Yeah, yeah. Part of them being ordered is you're never gonna have arrows that go straight across. Which one would be the cleanest arrows? So now all your arrows are going across. Unless you put them. I know. But then, yeah, but then what do you run out of comments using alphabet? It's not alphabet. Or, sorry. Right. And then also, would be best to put the person with the most because they're going to connect probably to those people. And then the travel distance is minimized. So you like Bell's purpose, like the ones with the highest and the ones that goes out.
And then you flip it on the other side. So it's the same.
But then the size. Yeah. Yeah. Napoleons. Yeah. Under. If you wanted, you could do if you wanted to go first on or something. Not, then you can have a direction go. Putting them in a ring out there. We have a lot of researchers.
Basically the object
Oh, that'd be nice. So then you encode like a ring, like a pie chart almost. Also, to reduce edge clutter, you could draw someone else that was sort of.
I think the thought okay. I don't know what you want to push there.
Yeah.
She was this is over here, Harvard. Yeah, you can start making them.
So you can have university.
Every source, every cluster.
Yeah, that's pretty cool.
project. And you can filter on here.
It's gotta be just a huge sample. What's that? Oh, okay.
Okay, on scale.
Or by topic. Partner.
Yeah, but this did not.
Each of these chunks would be a department.
Okay, only yes.
You can find the data.
Search by names. We don't want all these
For a lot of people's papers, they're affiliated, they're writing like IOC and papers.
You just have this name there.
You have new nodes. Yeah, you can search it.
And then you search his name.
Everything else appears, but it's
And then you just never know.
yeah, this is time traveling. Then you're just trying to like
You and you would connect with it. It would call it. It would be called. Same
Okay, so what kind of solutions did you come up with for this? Anybody want to just explain roughly what their ideas for solutions was?
We thought of doing kind of a donut chart where the length of the bar, the person correlates with how many papers they've done, and then there'd be connections between each bar as they've.
Okay, so you have essentially like a donut chart segment that represents a person, and then a link between the donut chart segments to show that they have co-authored something, and the width of that would correspond to the number of co-authors. Yeah? Anybody else want to talk about there?
Uneven, like, it's like an uneven matrix. So like each row, and I guess a column corresponds to a person, and then the size of like the square that each. So like each of their own like column and row overlaps, but that's a square and that's proportional to the amount of.
Yeah. So what we had right now was like a matrix layout where we have each person both as the column header and the row header, and then proportional to these attributes show the shows up like a glyph or a bar inside of those matrix cells. Somebody else had another idea?
So basically using each person as a circle, size of the circle would denote the number of papers.
Yeah.
We've got lines connecting each of the two nodes, basically co-authors.
Yeah.
So line would have a markation like how many number of papers are being collaborated, and we could use additional like the thickness of the line to show the variance in the papers.
Yeah. So essentially, like node persons as Pubble and the links strengths as the number of co-written papers. So this is great. You kind of came up with the most important two graph visualization techniques. There are node link diagrams, which the pi segments are, like here the pi segments are nodes, in this case the bubbles were nodes, and matrix layouts. So this would be like a simple version without much encoding of the node link layout, right? So I didn't bother, like you can encode the number of papers someone has written as the size or as the color or with an additional glyph in here. And then I have labeled the edges. We could also do that by width or something like that. Who has like drawn something along this line? Just a raise show of hands. So that's the way we think about graphs, right? We have nodes and links between them. And then the second approach is this matrix layout. Here, again, I have just like put the names in the columns, the names in the rows. I haven't really thought much about the graphical encoding for those numbers. I could do a bar in here or a color shape, and the same in here. The one thing that I've done here is whenever people have ever written a paper together, I have filled in the square, and then I have written a number on top of it. Again, there's many different ways of how we could encode this. But now let's look at those questions. How is Sean connected to Sylvia? So this is pretty easy to do, right? You simply trace Sean, Sylvia's over there. You kind of like look at what is the closest connection. So it's Sean, Alex, Mark, Sylvia. It's it's the shortest path. Or if you don't want to have the shortest path, you could say Sean, Mariah, Alex, Mark, Sylvia. And this is what's called a topology-based task. So we kind of traverse the graph mentally, we look for neighborhoods and so on. And so longer the distance, the tasks are easy to do in such a node link diagram. How is Sean connected to Niels? With this chart. Sean, Alex, Niels, yes. How did you do that?
On the first chart.
So this chart isn't really great at supporting this task, right? If you want to reason about path and something that is not in the immediate neighborhood, it's tricky. If I ask a question like, is Mark a co-author of Mariah? No. That's easy to do in this chart, right? Neighborhood tasks are easy to do in this chart because I simply have to look at, I had Mariah here and I want to know whether Mark is a co-author. I simply scan over and I can see exactly who are the co-authors. Are there, another question I could ask, is this network very dense? Is it almost everybody works with everybody? No. That's also easy to see here. You can also see that here, but I would argue maybe that this representation is a little bit more precise in terms of conveying this information. Who has the most co-authors? Alex. And you can also see this in this chart, but it kind of dominates the view a little bit in this chart. And so those are the two main visualization techniques for general graphs, these matrix layouts and the node link layouts. And I'll be talking about them for a fair bit now. But let's take a step back. And why do we need graphs? Why are graphs interesting? And I'm suspecting that I won't be getting much into graph visualization today because we only have 20 minutes left. But let's talk a little bit about why do we care about graphs. Graphs, it's not the standard data set, right? What software would you use to visualize a graph? Other than D3, obviously. But you can visualize tabular data with Excel or Tableau or something like that. But graphs are not as common, I would say, in the type of data that we have, but they're extremely common in nature and in very many scenarios. So graphs, essentially the internet is a big graph, and Google uses the PageRank algorithm, which is essentially a graph algorithm to identify important websites. We have integrated circuits, which are based on graphs. We have street networks, which are graphs. We have social networks, relationships, friendships networks, things like on Facebook or in actual real life, or on things like Twitter. What is the difference between the Twitter graph and the Facebook graph?
Well, it's kind of directed because you can follow someone and someone might not follow you back, but in Facebook you're saying...
Exactly. Facebook has undirected edges. You mostly there's now you can follow other pages and so on, but it's mostly you're friends with each other. There's not I'm following you, you're not following me back, right? And so that's the big difference between the Facebook and the Twitter graph. Here is a graph of Facebook where the nodes are geolocated. What is interesting, what's an interesting thing about this network? Where's China? China isn't there, of course, because the internet doesn't allow Facebook there. Networks are super important in biology. That's a research area that I work in a lot. Biological networks. For example, networks capture interactions between genes, interactions between proteins, interactions between proteins and chemical products, which are also drugs. And so, like, if you want to understand how a drug that targets a specific protein, like a specific process in a cell, it's not enough that you think about how it targets the one protein, but you need to understand what is going on in its environment. Because if you shut that protein off, there's other things that are affected by that. And that's the reason why we have side effects of drugs, right? There's no protein or no biochemical process in our body does only one thing. But if you have, for example, a drug for rheumatic arthritis also leads to sensitivity to the skin, because the same protein that is responsible for like something that is going on in our skin is also responsible for rheumatic arthritis. And so if you want to understand these trends, you need to understand graphs. Your ancestry is one big graph. The relations between you and your family, your parents, your grandparents, your uncles, and back to like evolutionary times. Phylogeny, the evolutionary relationships of life itself is one big tree. We have like these massive trees of life. Here's just a very simplified version where we divide it up into different kingdoms. Our brain is one big graph, like one big network of neurons that are connected to each other. Here we see a couple of neurons that are connected to each other in a 3D representation. This is from a mouse brain, and here's a very abstract representation of the same graph for one selected neuron. This is a network of biochemical relationships in the body. This is actually a wallpaper poster that you can print out and put on your wall, and then you would have like a little leaflet that tells you, okay, this particular chemical compound is found in quadrant A5, and then you can find it and look for it and then see what is going on in its environment, what is happening. So these are very intricate, very detailed, hand-drawn graphs that people actually use in pharmaceutical companies or in bio research in general. Here's like a nice TED Talk that I wanted to show 5 minutes of to kind of motivate how social networks impact our lives.
For me, this story begins about 15 years ago when I was a hospice doctor at the University of Chicago. And I was taking care of people who were dying and their families in the south side of Chicago. And I was observing what happened to people and their families over the course of their terminal illness. And in my lab, I was studying the widower effect, which is a very old idea in the social sciences, going back 150 years, known as dying of a broken heart. So when I die, my wife's risk of death can double, for instance, in the first year. And I had gone to take care of one particular patient, a woman who was dying of dementia. And in this case, unlike this couple, she was being cared for by her daughter. And the daughter was exhausted from caring for her mother. And the daughter's husband, he also was sick from his wife's exhaustion. And I was driving home one day, and I get a phone call from the husband's friend, calling me because he was depressed about what was happening to his friend. So here I get this call from this random guy that's having an experience that's being influenced by people at some social distance. And so I suddenly realized two very simple things. First, the widowhood effect was not restricted to husbands and wives. And second, it was not restricted to pairs of people. And I started to see the world in a whole new way, like pairs of people connected to each other. And then I realized that these individuals would be connected into foursomes with other pairs of people nearby. And that in fact, these people were embedded in other sorts of relationships, marriage and spousal and friendship and other sorts of ties. And that in fact, these connections were vast. And that we were all embedded in this broad set of connections with each other. So I started to see the world in a completely new way, and I became obsessed with this. I became obsessed with how it might be that we're embedded in these social networks and how they affect our lives. So social networks are these intricate things of beauty. And they are so elaborate and so complex and so ubiquitous, in fact, that one has to ask what purpose they serve. Why are we embedded in social networks? I mean, how do they form? How do they operate? And how do they affect us? And so my first topic with respect to this was not death, but obesity. And it had become trendy to speak about the obesity epidemic. And along with my collaborator, James Fowler, we began to wonder whether obesity really was epidemic, and could it spread from person to person, like the 4 people I discussed earlier. So this is a slide of some of our initial results. It's 2,200 people in the year 2000. Every dot is a person. We make the dot size proportional to people's body size. So bigger dots are bigger people. And in addition, if your body size, if your BMI, your body mass index is above 30, if you're clinically obese, we also color the dots yellow. So if you look at this image right away, you might be able to see that there are clusters of obese and non-obese people in the image. But the visual complexity is still very high. It's not obvious exactly what's going on. In addition, some questions are immediately raised. How much clustering is there? Is there more clustering than would be due to chance alone? How big are the clusters? How far do they reach? And most importantly, what causes the clusters? So we did some mathematics to study the size of these clusters. This here shows on the y-axis the increase in the probability that a person is obese given that a social contact of theirs is obese. And on the x-axis, the degrees of separation between the 2 people. And on the far left, you see the purple line. It says that if your friends are obese, your risk of obesity is 45% higher. And the next bar over, the orange line, says if your friends' friends are obese, your risk of obesity is 25% higher. And then the next line over says if your friend's friend's friend, someone you probably don't even know is obese, your risk of obesity is 10% higher. And it's only when you get to your friends' 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 friends that there's no longer a relationship between that person's body size and your own body size. Well, what might be causing this clustering? There are at least 3 possibilities. One possibility is that as I gain weight, it causes you to gain weight, a kind of induction, a kind of spread from person to person. Another possibility, very obvious, is homophily, or birds of a feather flock together. Here, I form my tie to you because you and I share a similar body size. And the last possibility is what is known as confounding, because it confounds our ability to figure out what's going on. And here the idea is not that my weight gain is causing your weight gain, nor that I preferentially form a tie with you because you and I share the same body size, but rather that we share a common exposure to something like a health club that makes us both lose weight at the same time. And when we studied these data, we found evidence for all of these things, including for induction. And we found that if your friend becomes obese, it increases your risk of obesity by about 57% in the same given time period. And there can be many mechanisms for this effect. One possibility is that your friends say to you something like, they adopt a behavior that spreads to you, like they say, let's go have muffins and beer, which is a terrible combination. But you adopt that combination and then you start gaining weight like them. And another more subtle possibility is that they start gaining weight and it changes your ideas of what an acceptable body size is. And here what's spreading from person to person is not a behavior, but rather a norm. An idea is spreading.
Okay, so this is just an illustration of how social networks influence our lives in many different ways. So let's talk a little bit about graph theory fundamentals in the last 10 minutes. There's a nice book that's online. This is by Laszlo Barabasi, who is kind of the scientist that essentially invented the field of network science, and so here's a link to that, which is a pretty interesting book. Graph theory goes back to the Königsberger Bridge problem, and the problem that was formulated sometime in 1736 is Königsberg is a city in Germany, and the question that people are talking about is, can you take a walk through the city, which was bisected by a river that branched? Can you take a walk through the city and visit every landmass without crossing a bridge twice? Try to figure it out.
Depends on where you start from. If you don't start from the island, there is no way you can, you will leave out a bridge or you will take a bridge twice in the island. Because there's 5 bridges.
Yes, but so you want to cross every bridge exactly once, sorry, that is imprecisely formulated. And it's not possible actually. And so Leonhard Euler formulated why this is not possible. First, he showed that it doesn't matter which path you take on land, right? So how you walk through the streets is irrelevant to answer this particular question. So we can abstract the land masses to vertices or to nodes. And then we can abstract the bridges as edges connecting those land masses. And so this would be the graph that corresponds to this Königsberg, the city of Königsberg, and the edges here would be the corresponding bridges across them. And then he showed that it's only possible with the graphs with at most 2 nodes with an odd number of links. And so this graph has 4 nodes with odd numbers of links, and therefore that's not possible. And so this is the first time that somebody has abstracted a problem into a graph theory formulation. And that's kind of what we think of as the first graph theory problem. If we talk about the graph in an abstract sense, we define a graph as G of VE, where V are vertices, which we also call nodes, and a set of edges, E, which we also call links connecting these vertices. The words graphs and networks are typically used interchangeably. What happens is that when you say graph to somebody who is not like a computer scientist or a visualization person, they think of like a chart. Network is usually the safer word if you want to talk to the general public. My distinction that I make is that I use the word graph if I talk about graph theory and the general graph, and I talk about networks if I talk about something specific. So it's a social network, but it's a graph traversal algorithm. So there's a couple of different classes of graphs. A simple graph is a graph which contains no multi-edges and no loops. So without the orange edges here, that would be a simple graph. With the orange edges, it would be not a simple graph. So we have self-loops and we have edges, like multiple edges connecting 2 nodes. A directed graph is one that discerns between edges from A to B and B to A. So this is exactly the difference between Facebook and Twitter that we mentioned earlier. A directed graph is Twitter, Facebook is an undirected graph. A hypergraph is a graph which edges connecting any number of vertices. Hypergraph is basically just a fancy word of saying there is a relationship between like multiple nodes at the same time. I like to think of those hyper edges also as sets. So if you think about like a social network, you could say all of your friends who are also at the University of Utah share a hyper edge with you. So you belong to one common thing, and this is also a set relationship on these graph nodes. There are graphs that can be unconnected, so it doesn't mean that just because you have different segments of a graph where there's no path between them, it is still a graph. And then there's special points in the graph. For example, an articulation point, and the definition of an articulation point is a vertex which, if deleted, would break up a connected graph into multiple subgraphs. Like here is an example. If I deleted the red point here, I would break up the graph into 2 graphs. And I don't think there is another articulation point in this graph. A biconnected graph is a graph without articulation points. So here I could delete any vertex without breaking up the graph. And a bipartite graph is a graph which vertices I can partition into 2 independent sets. And there's no edges within the set. So in this example, there's never an edge from a circle to a circle, or from a square to a square. There's always only an edge from a circle to a square. These are actually quite common as well, and they're also an interesting visualization problem. You probably all know what a tree is. A tree is just a graph with no cycles. Or you can also include the definition of a root in a tree. So in this case, like the right here is a tree that doesn't have a defined root. Most commonly, we think about trees having a root and then looking something like this. And there's also a recursive definition of a tree, which is as a collection of nodes which contain a root node and 0 to n subtrees, and the subtrees are connected to the root by an edge. And so here, like we have a root and then subtrees, and each of these subtrees has a root and then subtrees and so on. Trees can be ordered. Typically, we don't think of graphs as ordered, but we use ordered trees in many algorithms applications. So in this case here, if we consider this tree to be ordered, we wouldn't consider those two trees to be equal because the order of E and F here is different. As you can see here, for a general graph, those are, if you just look at the topology, those are identical. And there's actually over 1,000 named graph classes, clicks and trees and bipartographs and networks and hypergraphs and so on. There's whole books just on graph classes. So if you're interested in this kind of thing, you can take a look at this book. One very important measure about graphs are degrees. The degree of a node is the number of edges for a node. So here in this example, the node 1 has degree 1, node 2 has degree 3, node 3 has degree 2, node 4 has degree 2, because this is how many edges the graph has. Like an important measure about the graph is its average degree and its degree distribution. Like here we see the degree distribution of this graph. We see that there is like one node of degree 1, or like 25% of the nodes in this case have degree 1, 50% have degree 2, 25% have degree 3. This circle here, we have 100% of nodes have degree 2. What do you think that like social networks, what is the degree distribution of a social network, just intuitively? So many networks that we observe in real life, they have a very uneven degree distribution. There are central hubs in these networks. There's like, you probably have a couple of friends who have thousands of friends on Facebook, right? But most of your friends probably have like only 100 or 200 or 300. So here's a protein interaction network, and that shows us this principle of what's called preferential attachment, and this idea of a scale-free network also. So here is the degrees, the degree of the nodes, and the percent of nodes that have that degree. And you can see that about half of the nodes have a degree of 1 or 2 in this protein interaction network. I can't really read whether this is 1 or 2, but probably that's 1. And then about 20% have a degree of 2, and so on. And so this is kind of like a logarithmic effect that we see here, that very few nodes have very high numbers, a very high number of degree. Degree is a measure of local importance, and this is a network that I'll be using a lot to illustrate a couple of concepts. This is the Les Miserables network of characters that appear together in the book, and you see Valjean here is the main character, and he appears with lots of the actors, but not with everyone directly, right? Valjean never directly interacts with those people out here. He only indirectly interacts with them through Muriel. So degree is a measure of local importance, but a degree doesn't necessarily tell us how important a network is in the global network, right? Because like if you think about, for example, the internet, it would be easy to fake the degree of a network, but it would be harder to fake something like betweenness centrality. Betweenness centrality is a measure of a network of how many shortest paths pass through a single node. And this is like a good measure of the overall relevance of a node in a graph. And so here I'm plotting the betweenness centrality of these nodes. And so how betweenness centrality works is, like I'm looking for every node to every other node, what is the shortest path, and then I keep track of how many shortest paths go through a certain node. And you can see the nodes here are sized by the betweenness centrality, and there's a lot of shortest paths that go through Valjean. So this is a good measure for the overall relevance of a node in the graph. Here's a comparison for those two networks in terms of the histogram of the degrees. And you can see for the histogram betweenness centrality that we have even on the more extreme distribution, that the majority of nodes in a network have a low betweenness centrality, and then we have a couple of high outliers here. Path and distances. A path is a route along links, and the path length is the number of links that is contained in that path. Very often we care about shortest path, shortest path connect nodes I and J with the smallest number of links. And we also can define the diameter of a graph is the longest shortest path within G. So between any combination of nodes, which is the longest shortest path between them, that's the diameter of a graph. And that's also an important graph measure. And that's kind of the very short graph theory introduction, which is exactly at 3:20, and then we'll talk about visualization techniques for graphs. Well, next week we have Tuesday. Remember, there's a mandatory peer feedback session, and then on Thursday we have a guest lecturer who will be talking about medical visualization, or not medical visualization, but molecular animation, Jenna Diwasa. So please, Tuesday is mandatory. On Thursday, please make sure you come. A, she gives a great talk, and B, it looks really bad if there's only very few people for a guest lecture. Okay, thanks guys.